Electrical power engineering. Electrical power engineering is part of electrical engineering that covers conversion and saving of electrical energy. All electronic appliances are powered by different sources. These sources can be autonomous and portable or stationary. Autonomous sources are all battery systems and devices that power portable and autonomous devices. Generally, battery systems are only a way of saving the energy that we supply from stationary systems, such as electrical network. Completely autonomous energy sources are systems that are not dependent on energy from electrical networks and do the conversion of non-electrical energy into electrical on the given spot. Such sources are different solar cells, wind power plants, etc. On this spot, we can question ourselves, what is conversion and electrical energy control? Energy is needed for all human efforts. Capacity and flexibility of modern electronics have to be accepted as new challenges for efficient use of energy. It is crucial to think how electronic circuits and systems can be used for conversion and energy management. Electrical power engineering includes studying of electronic circuits that are intended for control and electrical energy current. These circuits manage powers that are significantly higher than the price of each device. Rectifiers are probably the most known examples of circuits that fall under this definition. Converter is a term used for a certain type of circuits and systems that convert energy. Converters are classified depending on the type of input and output electrical energy. We know AC-DC, DC-DC, DC-AC converters, and these are most often used as power supply units of electronic devices. Electrical power engineering presents the middle point where energy systems, classical electronics, and power steering are joined. This is further supported by the fact that all microcontroller systems, digital logic circuits or simple steering for their functioning need electrical energy. This energy is generated from electrical power engineering, that is the key domain of electrical power engineering. Each circuit for transmission and conversion of energy has to consider these issues from both perspectives, as control, and as energy conversion. The main topics of electrical power engineering are research on semiconductor elements, use of magnetic devices for energy saving, management methods that are part of modern energy systems. In each electrical engineering study, the importance of electronics has to be presented from the perspective of digital, analog and radio frequency electronics that reflect characteristic methods and unique challenges. Applications of electrical power engineering spread exponentially. It is not possible to build computers, mobile phones, automobiles, airplanes, industrial processes and many other everyday products without electrical power engineering. Alternative energy systems, such as wind generators, solar energy, fuel cells, and others all require electrical power engineering for their functioning. The technology advances, such as electric and hybrid vehicles, laptops, microwave ovens, flat panel displays, LED lighting, and hundreds of other innovations that could not be executed until the advances in electrical power engineering enabled their production. Although no one can predict future, it is clear that electrical power engineering will be in the center of core energy innovations. History of electrical power engineering is closely related to the improvements of electronic components that provide functioning with higher powers. Since 1990, the components and devices became so sophisticated that the transition from physical devices to program applications has begun. This transition was based on two key factors. For almost every application exist advanced semiconductors with suitable powers that are widely accessible. The main tendency for component miniaturization increases with the number of electrical devices and products. Although devices are still improving, their development follows innovative applications and devices. All electronic circuits regulate electrical energy current between electrical source and load. Components in circuit need to direct to electrical currents and not interfere with them. The function of power converter is a control over energy current between source and load. In our case, the power conversion will be executed with the electronic circuit. Because there is power converter between energy source and load, all used energy from the converter is distributed to all components inside the converter. Here is the key challenge. For building a converter, it is needed to use components without or with low losses. It is favorable that the converter efficiency is close to 100%. A power converter that is connected to the source and load also influences the reliability of the system. If the energy source is completely reliable, the unreliable converter can influence the load. Unreliable converter is on load seen as an unreliable power source. The unreliable power converter also causes unreliability of the complete system. If we take a look at this from the perspective of the source, we can say that average European household experiences electrical network failure only a few minutes a year. Energy is available 99.9% of the time. Energy converter has to be reliable because only this can prevent system degradation. Ideal converter execution must not cause any problems in device's lifespan. High reliability can be a more difficult engineering challenge than the high efficiency of converter. From the perspective of the ecological design of electrical devices, the converters of energy are one of the foundations for reliable functioning and device efficiency. Converter efficiency influences device life cycle. That is an important methodology for evaluating the ecological efficiency of the device. Switch mode functioning. Functioning of switch converters is based on low-loss switches, which are extreme requirements for electrical power engineering. In the ideal case, when the switch is on, it has a zero drop in voltage and will transmit full energy to the load without any additional losses. If the switch is off, it has unlimited resistance, meaning that no current will go through the switch. The power of switch is a product of voltage and current, meaning that the desired product of both values equals 0. If the power is equal to 0, we do not have any energy use on the switch element in the given time. The switch, therefore, regulates energy current without loss, where switch reliability is crucial. Household mechanical switches perform maybe even more than 100.000 switches in 1 decade of use. Unfortunately, the mechanical switches do not fit all practical needs. Electronic switches that are part of the power supply circuit switch even more than 100.000 times in 1 second. Even the best mechanical switches will not withstand more than 1,000,000 cycles. Due to this, we use semiconductor switches of selected powers in converters. Conversion system consists of 4 separate units, which are: energy source, converter's power circuit, unit for converter management, load. One of the energy sources in electronic device can be network voltage, battery, or other alternative sources. Power circuits differ by the converter type, which is differentiated depending on input and output voltage. We know converters that convert alternating current into one-way, AC-DC, alternate current to direct current. AC converter type is often used in electronic circuits that are powered by the electrical network and require a one-way current for functioning, logic circuits, one-way analog circuits, microcontrollers, computer systems, etc. AC-DC converter is also known as a rectifier. Another type are DC-DC converters, direct current to direct current. These are used for increasing or decreasing of one-way current. Electronic circuits and built-in elements for their functioning need different voltage potentials. With the use of DC-DC converters, we integrate voltage potentials in electronic circuits. The most common voltage potentials are 12V, 3.3V, 5V. The last converter type are DC-AC converters, direct current to alternate current. These are also known as power inverters and are used for conversion of one-way to alternating current. They are often used in alternating electrical engines with adjustable speed and conversion of energy from alternative sources, such as solar power plant. Converter's control unit can be in the form of analog circuit or with a microcontroller. The control unit is responsible for control of semiconductor switches, depending on the desired converter output. This can be voltage level, phase shift, or frequency of the periodic signal. Load type is conditioning the converter functioning and its control. For example, we know inductive or capacitive load that cause voltage or current edges and simple ohm loads that do not have a distinctive transitional appearance. We often see mixed loads that have resistance, inductiveness, but also capacitance. Known inductive loads are engines, relay, and power contactors. All converter elements are designed in order to have as low energy losses as possible. Switching devices are chosen by their capacities and desired energy transfer that is stated as a product of current and voltage. This is in opposition to other electronics applications at which we usually state power loss. For example, typical stereo receiver executes conversion of the alternating input voltage to audio output. Most audio amplifiers do not use electrical power engineering techniques where semiconductor components would serve as switches. The commercial 100W amplifier is generally designed with transistors that are big enough to transfer 100W of power. Semiconductor devices are used mainly for reconstruction of the audio signal, but not for manipulation of energy currents that cause significant losses. Amplifier for home theaters operates with efficiency below 10%. Contrary to these type of amplifiers, there are others that use electrical power engineering techniques for conversion of power. These techniques provide high efficiency. Home theater system that uses switching amplifiers can reach even 90% energy efficiency and have small dimensions. Often this type of amplifiers does not need additional cooling elements and are integrated into one chip. Amplifiers can even be built in directly into speakers. Power applications bring us to interesting questions and challenges. In converters where the main part are low-loss semiconductor switches, they often manipulate with 30-fold dissipation power capacities. This means we only have approximately 3% loss. A small error in design can cause unexpected heat losses, or a small change in element arrangement can drastically reduce converter efficiency. For example, if the loss is 4% instead of 3%, the voltage in the device is 33% higher, which consequently leads to device failure or error. Design of power converters can be summed with three main challenges. The first challenge is the reliability of power electronic circuits. We need to strictly comply with the nominal voltage, currents, and power delivered by the device. The power always has to be within limits. This is especially important when managing high powers. The second challenge is circuit simplicity. In electronic circuits, it is known that the more elements they contain, the higher the chance of error or failure of the complete system. Electrical power engineering circuits usually have many components, especially the main energy branches. For achieving converter efficiency, it is very important that we choose main components reasonably. This means that sophisticated management strategies are implemented with simple electronic circuits. The third challenge is integration. One of the ways how to avoid compromise between reliability and complexity is the integration of larger components and functions into one substrate. For example, the microprocessor can contain millions of gates. All interconnections and signals are running inside on the chip, and the reliability is dependent on only one component. An important trend in electrical power engineering is development of integrated modules. The manufacturers are searching for ways how to integrate as many important components into one module as possible. Miniaturization of components also creates new challenges. Many semiconductor elements contain small binding wires that can be sensitive to heat or vibration damages. Smaller geometries can also increase electromagnetic disturbances between internal components. A very interesting is a comparison of analog and switch converters. Switch converters are seen as devices with high efficiency, smaller dimensions, and high power in comparison to linear converters. They also do not need a complex cooling system. But these devices are more complex than linear and cause corrugated output voltage, which prevents the use of certain precise applications. Linear converters are nowadays most often used for lower powers as stabilizers of different electronic components. Here are some characteristics of both groups. Linear DC power supplies were widely used until the late 1970s. With technology advancement of switching power supplies, the linear power supplies are nowadays less popular but still used in applications that require non-corrugated and stable output voltage. Linear power supplies use a large transformer for the transformation of high AC voltage to low AC voltage. Next steps after transformation are rectifier circuits and different filters that create low-wave DC voltage. Low one-way voltage is then regulated to the given level with voltage stabilizers. The typical applications of linear power supply systems are audio technology, studio mixers, low-noise amplifiers, signal processing, data gathering with ADC converters, closed-loop management, precise laboratory equipment. Switching DC power supplies, these were first introduced in the late 1970s and nowadays the most popular type of DC power supplies on the market due to exceptional energy efficiency. Switch rectifier adjusts output voltage with pulse width modulation (PWM). The PWM technique creates high-frequency disturbances but enables that electrical voltage is produced with very high power efficiency. With a good design, the switching voltage has great disturbances regulation and line load. The typical applications for switch DC power supplies are high voltage and current applications, mobile and communication devices, battery charging for different devices and vehicles, one-way motors.